Hello, 9 a.m., dreadful hour, but thanks for coming to my talk. I'm Michal, I work at Kado Technology, and I'm going to talk about practical side of streams. A quick show of hands, who actually knows what streams are? Thanks. So I'm not going to talk about Java 8 streams. I'm going to talk about a slightly different concept, sometimes called observables. We are going to create a multiplayer web game using streams as building blocks for both front-end and back-end parts. And the game itself is a classic Snake, the one that some of us and you played on Nokias back in the days. And we are going to show many code snippets and diagrams, different technologies and libraries. So whenever something's unclear, please ask questions. What are streams? Those streams are just yet another way of defining application logic. Those are also a model, a concurrency model. And from those on the slide, streams are most abstract. Why? Because we are focusing on data transformations. And the square in the middle, the gray one, is the only user code, the only code you write. You just take one element and return another one. So that's why streams are the most abstract of those concurrency model. And when you think about data, you think about usual suspects like ints, floats, right? Arrays, lists. But surprisingly, code can also be data. So you will see streams of functions and how those can be applicable. What's crazy cool about streams is that they help us fight with our worst enemy, the time. When you are programming using streams, you don't care about what has just happened or what will happen next. You just care and you just focus on what's happening right now, what is happening right now. Once again, you only care about the current data transformation. The diagram on the slide, I will use this diagram throughout the whole presentation. Time flows from left to right, and those circles are elements. In this case, empty elements. That all means that we are becoming declarative programmers. We are programming using descriptions, not instructions. That also means that we have more testable code because we are using pure functions more frequently. The talk consists of 3 parts. In the first part, we'll create a front-end part of the game using JavaScript and JavaScript streaming library. Then we'll move to the backend part, and we will create a multiplayer backend using Akka streams and Scala. And then to cool things down, I will do a short introduction to reactive streams. How do they differ to the streams from the first 2 parts, and how do they make asynchronous communication safer? Okay, let's meet characters for today. The gray area is the board, the red square is the fruit, and the green square is our protagonist, the snake. And the first stream is just stream of empty objects that appear every 100 milliseconds. So this is the building block for the whole game. This will make everything move around without players touching any keyboard keys. So this is the first stream. We'll call this stream ticks. What we can do with the stream is that we can map over it. And map is the first stream operator that we'll meet from 6 that I want to introduce today. So we are putting tick stream as our input stream to the map operator, and map operator generates another, yet different stream that has all the values from the input stream, but mapped with the function we provide. In this case, the function is just a function that returns vector 0, 1 every time it's called. So what we get as an output, as generated stream, is a stream that outputs 0, 1 vector every 100 milliseconds. And we'll call this stream direction stream. Then we can take this direction stream and scan over it. So this is the second operator. And I will do a short summary of those two operators in the next slide. But for now, let's assume that scan is just an accumulator. So it accumulates value over time. That's how we can convey the information that changes over time without using any assignable variables. So what this means here is that vector 0, 0 is our initial value. And this function is called every time there is a value inside input stream. So whenever a value 0, 1 appears here, we are just calling this function, and the current accumulator value is position, and current element from here is direction, right? Because this input stream is direction stream. And the function returns a position with direction vector added to it. And as you can see, there is 0, 1, 0, 2, 0, 3. And we'll call this stream snake's head positions. So right now, our snake should move only from top to bottom, and that's all. Let's quickly sum up those two operators from 6 that we'll introduce today. Map transforms values from input stream using the function we provide, and scan accumulates values from the input stream using the function we provide. Every time the accumulator changes, its output on the generated stream. And this is how the code, real code from JavaScript, written in JavaScript looks like. So as you can see, the diagrams are mapped directly to the code. So ticks is just interval 100 milliseconds. So this is our stream of empty objects. Directions is the tick stream mapped with this function that returns 0, 1 vector. And snake head positions is just direction stream that is scanned over with this adding vector function. Okay? And sorry about that. And what we can do with the values in snake head positions, we can pass them to a function each time there is a new value. So every time there is a new value in the snake head positions, we just send the value to the display function. And what display function does, it just displays the current element. We are using React.js here, so it's also a declarative front-end library. Two things about streams that are worth mentioning right now. First one, streams are reusable. So what we did here is we just displayed every value from this stream. But we can reuse the same stream, snake head positions, and for example, send the value to the server and persist it. And this all will work fine. And the other thing is that if there are no such terminal functions, because onValue is called terminal function, or there are no elements at all, there will be no CPU cycles. So there will be nothing happening inside the streams. Yeah, and this is how our game looks like right now. The snake is moving downwards, and the player has no control over it. So let's change it. Let's introduce another stream, this time a key presses stream. Each time user presses a key on the keyboard, the value appears in the stream. And the object value is the keyboard event, right? So every time user presses a button, any button on the keyboard, the value appears in the stream. How can we use that? We can create a left key presses stream. And using the third operator filter, we can just filter out all keys besides the left key, right? And what we get is left key presses stream. Every time a user presses a left key, we have a value in the stream. The same can be done for right key presses. So we can reuse the key presses stream and filter out all the key presses besides the right key. And the filter is the third operator. As I told you, it checks whether the value that appeared in the input stream, the value matches or passes the predicate P. And if it does, then it's output to the output stream. Okay, let's continue. Now the things are getting crazier. Keyboard left rotation stream is what we create by mapping left key presses stream. So this is left key presses stream. This is input stream. Every time user presses a left key, the object keyboard event appears in this stream. We can map every value in this left key presses stream with this function. What this function does, it returns a function. Again, it returns a function. So what we get here is left rotation stream. And just to wake you up, what is left rotation stream? What it conveys?
Turning the snake to the left.
But what's that?
That's the value of the function.
That's the value of a function? What do you mean?
I mean, it passes the function to the stream.
So this stream,
Yeah, every time the stream, like the event is called, then that function is going to be called.
not really, this is a value. This is a value, but the value is a function. So this is a function without passing any arguments yet. So this is just like a real function. We can call this element, but because it's a function. So what this stream has, it has functions inside it. Every time user presses a left key, in this case, a left key on the keyboard, the generated left rotation stream will output a function that we need to use in order to transform the direction. But the function is not used it's not yet used. The same, we can do a similar thing with the right rotations. So we can map right key presses and we'll get rotate right functions inside. What we can do next is we can merge left rotations and right rotations together and we'll get action stream. So anytime, how the merge works, anytime something appears on either of those two input streams, the value is also output to the output stream. And the action stream, if we just translate it to the business kind of talk, what it means that every time user wants to change direction, the action stream will contain a function that we need to use in order to transform this direction. Okay? Nothing more. So again, merge. Anytime something appears on stream or stream 2, it will also appear on generated stream. Okay, so now we can do a new direction stream. The old one was, as you remember, just 0 ones every 100 milliseconds. And now we have user input as the main input. So we have action stream, rotate left, and we can scan over the stream of functions. And please pay attention to the slide. So what we are doing, what scan does, it accumulates values. This is our initial value. So this is our initial direction, 0, 1, as before. But right now, anytime something appears in the input stream, which is action stream, anytime something appears in the action stream, so the value here, f, we know that action stream conveys functions. So f, whenever something appears here, it's passed to this function as f. And the dir is our current accumulator value, which is initialized with 0, 1. And what the function does, it should return a new accumulator value, right? Just as before. And in this case, new accumulator value is just a current accumulator value passed to the function, right? So we are transforming the current accumulator value, which is direction, with a function that is provided in action stream. And this function appears in this action stream anytime user presses a left or right key. Okay, any questions about that? Everything's clear? This is the hardest part, so if you understand that, later things are far easier. Okay, so if you understand everything, let's see whether you can answer this question. This is the old direction stream, 0, 1 in each 100 milliseconds. And this is our new direction stream. So what's the difference? What did we lose? Sorry?
Time.
Yeah, we lost time, right? What happens here is that the direction in the old case, direction changes each 100 milliseconds. Direction changes, doesn't change really, but it's still output to this generated stream. So each 100 milliseconds, we get the current value of direction, and this causes our snake to move without touching the keyboard. In the second case, we have user input inside the stream, but the direction changes and is output only when the user changes it. So the snake will only move whenever you change direction, which is not what we want. If you remember correctly, when you change the direction in snake game, it should move towards this direction until it's changed again or until we lose the game. So let's introduce a new operator, second to last, sampled by. What it does, it takes two streams as an input. The first one is value stream, and the second one is sampling stream. Anytime something appears in sampling stream, we get the last value from value stream and output it. It's better shown using this kind of example. So we have our direction stream at the top here. Anytime user wants to change direction, the direction is appearing here. And we have our tick stream as sampling stream. So as you see, anytime there is a value in sampling stream, the last value from direction stream is being output here. And sometimes we lose information, right? Because in this case, we appeared 0, we output 0, 1 2 times, and 1, 2 vector appeared once, 1, 1 has never appeared. So what we got is we got a real direction stream. We have a direction changes by user, and we have timing provided inside it. So this is what moves our game. Okay. Now the cool part is streams are reusable, and we reused direction stream in snake head position stream, and now we don't really need to change it. It will use just new direction stream, and the position will be properly output. This is how it looks in the code. I'm not lying. This is all we need in order to implement our business logic. So again, our key stream here, left key presses, every time user presses the left key, it appears here. Right is just keys filtered with this kind of predicate. Then left rotations return functions and rotate left and right. And we can merge left rotations with right rotations, and we get actions. And then we can scan over it and have directions or new directions. So what you've seen on the slides and on the diagrams is directly mapped to the code. So this is what we have right now. Current implementation using 10 streams and 5 operators. So user can move around, and the snake does what the user wants it to do. Let's make the snake bigger. We can use another operator, which is sliding window. What it does, it just gets last n values from the stream, input stream, and outputs it as an array of those values. So if we have our snake head position stream as input, we can use sliding window 2, and we'll get snakes of size 2 here, right? And the second thing before the live demo of the front-end part is the quiz for you. How can we implement eating a fruit? What I want to do is I want to have a stream which outputs a value every time snake eats a fruit. And fruit is just let's assume fruit is just a constant value, so you have access to it. And what operator should we reuse and what stream should we reuse from those on the slide, from those which we've used so far. 20 seconds to think. Again, I want to have a stream which outputs a value, any value, anytime snake eats a fruit. Anybody? Great. You have to filter the snake head positions. Great. Thanks a lot. And so we input stream for the filter is snake head positions, and anytime snake head position equals the fruit position, we just output it, right? And we don't output anything more. So that's why we can have a stream of fruit eaten events. Anytime fruit is eaten, we have an object inside the stream. Thanks a lot. So let's see frontend in action. Let's see the frontend in action. Yeah, so the game is started, and yeah, I'm getting pretty good at this moment. As you see, oh no. Okay, yeah, it works, right? So this is the code I've shown you is the really the only business logic. All the other lines are just front end displaying, styles, things like that. And the whole project I will share. It's on GitHub, and it takes 100 lines or so. So that's the power of declarative programming. Okay, let's move to the server part. But before we do that, I want to quickly wrap up how we did the front-end part. We did it bottom up, right? So we just started with small building blocks, and we composed them together in order to create a game. But the whole architecture looks like that. So we have 11 streams, and each of those blocks are a stream, and each of those arrows are a streaming operator, like map, filter, right? So we have ticks, stream, and we can get direction stream from it by mapping, right? For example, or by mapping and scanning. And the two streams here, ticks and keys, are the only streams that use outside world values in order to produce their values. And the other streams are using only other streams as input, no values from the outside world, which make them more testable. And the right outmost streams are the streams whose values are used by the outside world, not by other streams. So you can see that ticks uses clock, keys using user input on the keyboard, and snakes and fruits are used by the outside world, like browser rendering, things like that. And yeah, let's go multiplayer, and we'll see some Scala code, no JavaScript. I know that there are not many fans of JavaScript in the industry. Okay, let's do it. Who of you like JavaScript? Yeah, okay, 7 people, 8. I assume the other ones don't really like it at all, and there are no gray parts, right? Okay, the requirements for the server part. Clients send positions to the server. So we have each frontend, so we have, for example, 2 players. Each runs the application I've shown you, and the application should, anytime snake position changes, should send the position to the server. And the server is responsible for generating the fruits, right? Because it needs to know who's there first, and should keep scores and broadcast all these things to the clients. Positions of the enemies, the fruits, and the scoreboard. And I think that we can use streams, because as you see, those are really cool things to do in streams. So let's do it, but this time top-down. Top-down means that we start with a flow. The general architecture I've shown you before is just a flow, right? So streams connected together. So this is a general flow we want to implement. This is one player flow. So we'll have, for 2 players, we'll have 2 instances, but the flow will be the same. Player states here on the left, this is something that we need to receive. And player states mean a name of the player and the snake position, all the squares that consist of to snake. And what we get in response from the server flow is we should get a game event, which consists of players states, so other players states also, names and their positions, fruits, stream. Each time there's a new fruit, there should be a value in this game event, and scores, which just is a current scoreboard. And what we want to implement is this question mark here. But before we do that, let's focus on technicalities. So we can use WebSocket connection, one WebSocket connection per player in order to transmit those things. Player states can be sent down the WebSocket connection to the server, and server should reuse the same WebSocket connection and send back player states, fruits, and scores. And this is how it looks in Accessory's code. And who of you was on my talk yesterday? Okay, so this again is a route that we use in order to specify web server. But what we get here is a helper function, handle WebSocket messages. What it does, it receives a flow, a real flow, that is the implementation of the WebSocket connection. And this is just a business implementation. So this is our question mark from previous slide. And this is all the boilerplate you need. So you just bind to the interface and use streams, so the flow, a connected flow of streams, in order to implement the logic behind WebSocket. So anytime frontend part connects to our server with snakes on snake socket path, it opens a WebSocket connection and uses flow to support that, to serve that. And this is the general architecture of the application. Client flow, the small things here you cannot see, is the thing I shown before. So this is just the front-end part. This is the WebSocket here, and this is server flow. So as you can see, we use WebSocket in order to reuse more than one streams, but that's okay, that works fine. Player states are sent to the server, and all the other things like other player states and fruits and scores are sent back. And we'll go through those 4 squares in order to implement our question mark here. So let's start with the fruit. So fruit eaten events can be just directly moved from the front-end part, because it's also head position filtered, and we get an object. So this is directly transferred from front-end to server, but just a different technology, though the filter operator works the same in both. Then we can use this eaten event stream and map over it with a function that returns a random vector. This way we can get a new fruit. So this can be a little tricky, but this is just for demonstration purposes. So this random vector doesn't really pay attention to where all the other snakes are, right? So it can generate value on the snake. So yeah, it's not very robust right now, but just for the demo, it works fine. And because we need a head to eat the element, not the tail. And yeah, so you can see anytime there is an event here, anytime somebody eats a fruit, we get a new value of the fruit here. This is how it looks in Scala code. And what I need to introduce right now is this flow type here. So flow type is just a block with one in and one out. And the types of in and out are provided in the type parameter list. So the fruit flow, what it gets as input is list of player position. So a snake, the whole snake, all the positions that are snake positions. And what it gets out, it's a fruit position. That's all, right? And we can map asynchronously using a function that returns fruit position based on player positions. This is how it works. So this is the type of fruit flow. So this is our first building block for the question mark block. Okay, any questions? What was the underscore parameter on this slide? So we are not using it here, but this is a materialized type value. When you create a stream, before it's even run, it produces a value. For example, some information, some metadata, but you can reuse this value in order to set up other streams. We don't use it here, but yours, when you create a flow, you can provide something like that in order to be more configurable, okay? Fruits are done. Now let's move to the scores. We can reuse eaten events again and map over it with a function which always returns 1, and we get a score update stream. What score update stream has is it has value. Each time the value should change, it has the int value that we need to add to the score, right? So it's 1, and every time the player snake eats a fruit, we have a value of 1 in the stream. What we can do with it? Scan. You are good at that. Really? Yeah, of course. We can scan over it with a simple summing function. Initial value is 0, and the function here has an accumulator value of score. A score is accumulator value, and up is the current element in the score updates stream. What we get is anytime score changes for this particular player, we get a value of the current score. This is how it looks using Accessory. So again, you can see a float type. The input type is fruit position, and we return int from this flow. So whenever we have a new fruit, we just return 1. Whenever we have a current fruit, we return 0. And then we scan over with the function that sums them. That's all. So this is the same as here. So we are done with scores, and this is how the game logic server looks like. So it's not as big as the front-end one, but it does its job. Player states are filtered in order to get eaten events, and eaten events are reused for score updates and fruits. Score updates are used for generating current scores. And game logic flow using Accessory. This is a comment for the method using GraphDev's DSL. I will show you this in IntelliJ in a bit. And I don't know if you can see properly. Probably. So what it does, it just transforms this diagram to Accessory's DSL. Because flow that we use so far is just 1 in and 1 out. So for example, if we need something that is 1 in, 2 out, we need a broadcast block, not flow block, but broadcast block, right? So we need to broadcast player state because it's used in 2 different places. And the same goes here. We have broadcast fruit position because it's used in 2 places. And the other way around, if we have multiple ins and 1 out, we use zip block, which is used here. So we use game event zip in order to zip all the things that we generated. And this is how it looks in the code. And you may be surprised that I still use flow. Why is that? Because as you see, the whole flow, even though it's inside it's more advanced, it's still just 1 in and 1 out, right? So I can wrap it up with a flow type and reuse it in different places. So game logic flow is still 1 in, 1 out flow. It gets player state and returns game event. But inside it's a more advanced graph using GraphDSL. So we just connect all the things, all the outlets and inlets together in order to produce this one simple block that we can reuse. Okay. All right. So this is how the Snake application for one player looks like. Client flow, server flow, and fruit and scores are done. We just need to take care of players' states. So we need to inform the current player, because this is one player flow, what are the positions of other players. And in order to do that, we need to cross asynchronous barrier here. So the flows are just, WebSocket connections, different for two players, two different WebSocket connections. So we need to generate something that will broadcast the information and can be received in other WebSocket connections. So this is this is a tricky part. So I just implemented it as one flow block that can be reused, but you can see how this looks like in the GitHub repository. And now we can connect all the dots together and create a flow which is passed to the WebSocket, handle WebSocket messages. This is a flow which gets a message, which is a message is WebSocket message really here, and outputs a message. So as you've seen before, one connection is reused to send things to the server and send things back to the client. And we just log all incoming traffic, then collect the text from the WebSocket message, parse the JSON, and convert it to player state, which is our case class that we use in the flows. And then we pass it via game logic flow, which is all the advanced things that are scores and fruits. Then via game event broadcast, which is this advanced block that just broadcasts the positions to other players. And then we get game event back. So we just parse it to JSON, to string, and map it to text message, which is a WebSocket message. So this is our whole application, really. And those building blocks here are defined in other places, can be tested in other places, and we just reuse all the stuff here. Let's see it in action. Yeah, so all those things that were on the slide: fruit flow, score flow, game logic flow, and game event broadcast flow, which you can, this is a tricky part, more hackery stuff, and the flow which connect all those things together. So this is 100 lines of code for the whole server application. Let's run it. And let's move back to the client here. Let's connect again. The same application as you see, but right now it shows score 0-0. I'm just one player. The other player hasn't joined yet. So what I can do right now is to get some score up so that the other one has no chance with me. 5-0. And let's go to the second player. Yeah, and as you can see, this is how it works. And when you go back to IntelliJ, you can see that there are some things going on here. So the log incoming here really does work, and we get all messages here. Okay. This is backend in action. So now the cool down part. Let's imagine that there are thousands of players. There are games like that, like Infinite Board and thousands of snakes. The bottleneck of our solution is that we need to merge all. We need to send all the players to the browser. So what it does, it doesn't work really if we have more than several players, because it's too much for the server to handle. And our application so far is constructed using Akka streams, and let's see how can we use this information in order to have a safer communication between frontend and the server. So crossing async boundary. What is asynchronous boundary? When two asynchronous systems communicate with each other, they need to cross this asynchronous boundary. And there is no other way around it. Those systems are working independently, and one of them will be faster. If they are asynchronous, one of them will be faster, even slightly, but faster. And we have two models that we use in order to handle crossing asynchronous boundary. One of them is push. And push is not safe whenever subscriber is slower. Why is that? Because when a publisher publishes messages with very fast pace, and the subscriber is very slow to handle them, then we will get out of memory at some point. Some of the buffers will overflow, and there are buffers everywhere. We need to be aware of that. However, this model is perfect when a subscriber is faster, right? Because the situation with the memory will never appear. Publisher can be very, very fast, but we know that subscriber is faster. So we have a perfect solution because the system works as fast as possible with no overhead. On the other hand, pull model is something different. Subscriber needs to ask first before the publisher produces and sends down the element. So this is too slow when subscriber is faster because we need to send two messages in order to convey one piece of information. However, it's perfect when subscriber is slower because what the please message does, it just slows down the publisher. Okay? And reactive streams are really trying to connect those ideas together. So what we get is the streams that are as fast as possible, but not faster. So this is a very simple idea, right? Consumer wants to pull elements, generates the demand, and only then publisher can push the elements to the consumer. What's different here is that the consumer can say, I want 5 million elements, and then the message, this is the only please message that exists there. And the publisher knows that it can send down 5 million elements at any pace it wants. Sometimes reactive streams are called streams with supply and demand. And you may have encountered another definition, which is back pressure. This is the same thing, but not the same thing. This is a similar thing, but a lack of demand means back pressure, right? So whenever you say please or don't say that you want new elements, you are basically saying please don't do anything. So you are back pressuring the publisher. And example, we have 4 asynchronous systems here, and the publisher, the subscriber, and 2 processors. Processors are publisher. One processor is publisher and subscriber in one system. So as you see, first subscriber, nothing happens until subscriber generates the demand, right? So this arrow here means demand, and nothing happens. What the whole system does is that it forwards demand upstream. So from subscriber to this processor forwards it to this processor and to the publisher. Then publisher can produce the information and generate the value. Or 5 million, or the message conveys an information about how many can the publisher really publish or send or generate and send. And then after that, only after that, the publisher can send data downstream until the demand is satisfied. Okay? Now, a simple question for you. What if the processor here doesn't implement reactive streams? So it's just, a synchronous system which can receive and send information whenever it wants without paying attention to demand. What happens if only this one here is not reactive streams compliant?
And I'm not sure if it forwards the demand message.
You are not sure, and I'm either not sure because it is not compliant, so it can do whatever it wants. So what then? How can we think about the whole system? Is it reactive stream compliance? No, it's not. So it's all or nothing. all the systems, all the asynchronous systems need to implement the reactive streams properly in order for the whole system to be safe. So you not get any out of memories anywhere. Okay, so there is a protocol, reactive streams protocol, that anyone can implement so that many systems can work together and be compliant with reactive streams. This is just 4 classes and 7 methods. Really, the jar, the reactive streams jar, is just this, the whole API, 4 interfaces and 7 methods. This is all you need in order to implement the behavior I've described in previous 3 slides. And this seems pretty simple, right? But when you go to the GitHub, each of those methods, 7 methods, have like 17, 20 different corner cases that you need to be aware when you are implementing that. For example, while the subscription is not cancelled, calling subscription cancel may cause the publisher, if stateful, to transition into the shutdown state if no other subscription exists at this point. And C19, so another method for more details. So it's very, very hard to implement properly. But you can do it. And when you implement all those methods and interfaces, there is a TCK, Technology Compliance Kit, and you can use that in order to check your implementation, whether it's really compliant with reactive streams. And you know what, when you made errors, and after a few weeks, maybe you will have a working implementation, or maybe not. But safer bet, is to reuse the current implementation. So other projects and companies have already implemented reactive streams properly, and they are compliant. We used Akka streams, but JDK9 will also have the implementation of reactive streams. There are some integrations for Kafka, Mongo, and Cassandra, and of course some other projects like Vertex, which is a polyglot library, Slick Ratpack, and Project Reactor. Okay. Now the Akka stream model which we used, what Flow, you've seen Flow many times in this presentation, it's just a processor. Processor is publisher and subscriber in one. It's one in, one out, right? So it makes sense. Source is a model for publisher and sync for subscriber. So each of those library add another layer of abstraction over the reactive streams. But under the hood, when you go into the code deeply, you can see that they really implement the things from reactive streams jar, those interfaces. Yeah, so our Snake implementation uses the reactive streams API, but we didn't know about it. And having known that, do you think, can you answer this question? Is Snake multiplayer safe? Snake multiplayer is safe in your opinion? No? Why not?
Because you can send events.
Exactly. So frontend is pushing every 100 milliseconds, right? You've seen that. We just implemented ticks, and each time Snake position changes, it's pushed down to the server. So the client really doesn't care about the demand from the server. And server doesn't really send anything back to the client. This is because JavaScript libraries are not yet compliant with reactive streams. There are works in that area. So some of the web frameworks like RxJS will probably be the fastest ones to implement that. And yeah, maybe then we can just do an application like that and it will be safe right away. But not yet. What we can do is we can use more stream operators like conflate or expand. What conflate does, it just sits just before the server, and when there are thousand messages and the server just wants one message, the conflate does some calculations in order to transform those 1,000 messages in one. For example, dropping all the others or doing some average calculation, something like that. So it's totally based on your business logic. expand is the other way around. And of course, you can have a buffer, a safe buffer, which has a strategy when it's overflown. Okay? Those are the links that you can use. You can build your own snake using streams. And there is a blog post about that that takes you step by step. There's a client code, server code, and GitHub repositories. And there's this one library, RX Marbles, that I like to use whenever I want to learn new operators. So there are many libraries, streaming libraries. The operator names are different, but they work basically the same. For example, for merge, you can play around here. You have 2 input streams, and you can play with both and see what happens in the output streams whenever something changes in the input stream. Like scan, right? The most difficult one, which aggregates values. You can see that, for example, 1, 3, 6, 10 is the sum, but when we move 4 over here, the value of the output stream changes. So this is a cool tool in order to learn about those things. Yeah, and Akka streams and Bacon.js on the JavaScript. This is what I used. Thank you. Are there any more questions? If not, cheers and have a nice second day of conference. Thank you very much.